Hi, I'm Matthew Williams. I'm the CTO of Rockport Networks. Rockport has created a new switchless network architecture focused on meeting the high performance requirements of advanced applications. We've also removed a lot of the complexity typically associated with high performance networking. We're working with 7 of the leading high performance compute leaders. We're engaged with 5 of the top 7 storage OEMs, as well as 2 of the top 5 compute OEMs. I'd like to talk first about network congestion. When we're talking to customers and partners, this issue comes up time and time again due to the broad impacts it has on the entire HPC environment. First, network congestion will drive high tail latency. And of course, high tail latency will cause extended and unpredictable workload completion times. And it also limits the scale of the workloads. As workloads get larger, the amount of communication increases, making these workloads much more sensitive to network congestion and latency than at smaller scales. As well, with workload performance being impacted, research scientists must wait longer for their results. In terms of capacity, because each workload is taking longer to run, fewer workloads can be run in any given amount of time, which of course means that job queues get extended and research scientists must wait longer even for their jobs to start. From an efficiency point of view, when workloads are taking longer, that means for some of the time, the cluster resources will idle. Of course, these are very expensive resources, which means that the costs of running workloads have gone up. And when you look at the overall return on investment of a high performance cluster, that means you're running fewer workloads over that amount of time, which means, of course, the ROI has gone down. Now let's talk a little bit more about what congestion is and 2 different types of congestion, what we call short time frame congestion and long time frame congestion. Here I'm showing free flows of packets in a multi-workload environment arriving at the same switch, and all these packets are being forwarded to the same output port. And there are too many packets coming in for the switch to be able to send out this port. And in very short time frames, the only thing the switch can do is hold on to those packets in a memory buffer, which of course means that as you're waiting in the buffer, the latency has gone up, your tail latency goes up, which means your workload completion times are extended, and you're impacted by all those issues we just talked about. If the contention of that switch port lasts long enough, the switch can do a couple of things. The first is that it can use flow control to push back on some of the flows to slow them down. It can also steer the traffic away from the impacted switch. But one thing that's very important to understand is that all congestion starts out as short time frame congestion, which means the performance of your network is only going to be as good as your short time frame response. Rockport has created this switchless network environment where instead of centralized switches, we've moved the switching function down to each endpoint, creating a direct interconnect architecture where each of our nodes is directly connected to 12 other nodes. We've also moved some of the key network functions, source routing as an example, down to each of the nodes, making them self-discovering, self-configuring, and self-healing. We've also, the embedded flit switching allows the nodes to forward traffic across the network. Because a lot of these functions are distributed down to the endpoints, that means that we have perfectly linear scaling, as we're not reliant on spare capacity being available within centralized switch architecture, which means that we can grow in place within a cluster as we needed. So our switchless network solution is composed of 3 major elements. The first is our network card. We call it a network card instead of a network interface card because it provides not only the host interface, it also implements the switching function. We present a standard Ethernet interface with broad application, use case, driver, and software library support. Now, flit switching is implemented within a field upgradable FPGA. We have a rich roadmap of features and performance enhancements. Out of the network card is a 300 gigabit per second, 12 by 25 passive fiber optic cable that goes to the second element in our system we call a shuffle. And the shuffle is a completely passive device. There's no power, there's no moving parts. We've simply pre-wired very powerful supercomputer topologies within this box. Think of it as an advanced patch panel. So that when we plug in the single cable, the network operator has created a supercomputer topology. The cards self-discover, self-configure. If there's any issues in the network, we of course self-heal. We also provide an autonomous network manager that provides deep insights into the operation of the network environment. And all the information that we measure and monitor is stored in a database for up to 7 days, which means that network operators can go back in time to view network performance and network status when workloads were running after the job is completed. One of the key aspects of judging how well a network will run is seeing how well it will run when loaded. Typically, network benchmarks are run in unloaded environments where there are no other traffic on the network. So what we like to do at Rockport, and our customers and partners have the same approach, is to run the benchmark tests in both the unloaded environment and in a loaded environment. Here we're showing the performance of Rockport in an unloaded environment with 20 runs of the OSU latency benchmark, showing excellent latency performance over a broad range of message sizes. On the right-hand side is the exact same test on the same system, but this time we've added 5 pairs of adversarial traffic generators in order to heavily congest the network. You can see from the table that our performance under load is excellent. There's less than a 0.1% latency impact due to this congestion, which means in a Rockport network, critical message performance is immune to any network congestion, even when it's extremely heavy. This leads to, of course, consistent workload completion times, better cluster efficiency, and higher cluster capacity. So to summarize, there are many costs of congestion. It's not just a network issue. It's a workload performance issue. It's a cluster efficiency issue. And the key performance drivers within a network are how you respond to short time frame congestion and how you perform in a loaded environment. Rockport has a new switchless direct interconnect architecture that's designed to deliver high performance at scale under load in a very simplified manner, allowing advanced supercomputer topologies to be leveraged by all end users. Thank you.